Okay. So yesterday we had stopped at this point. I think we had seen dp dt is equal to delta S transition by delta V transition, right? And that was the Clapeyron equation. And this is this is an exact equation, okay? We've not put any assumptions over there. So now what we have to worry about is that, can I simplify it? Okay. By the way, this is delta S transition molar values. Okay. Just keep in mind. So what I have to worry about is that delta S transition, the temperature is constant, heat is being exchanged in this transition, maybe it's melting or boiling, which means I can write this as delta H transition by T and then delta V transition. And I know that this fellow is positive, and I know that delta V transition is positive if I am talking of melting or boiling or sublimation. If I worry about the other way around, then mostly it's negative, right? So what I have to then worry about is that what would be the slopes out there. So if you look at the phase diagram, pressure versus temperature, then this slope is positive definitely. This one is also positive, and for most systems it's a positive slope out there as well. Let me mark that: solid, liquid and gas. So dp by dt is a positive number, except for the case of water, which we've seen. In case of melting or for the solid liquid equilibrium, that's a very small negative number. So how do I calculate this? So the idea was to somehow predict or somehow be able to make out these equilibrium lines. Now can I account for it? That was the idea. So in case of a solid transformation, I know it's a straight line, so I should get a straight line equation, of course. And I know that delta H of fusion is some finite number, okay? And delta V of fusion would be a very small number because the volume of solid and the volume of liquid are not much different, right? They are small quantities. These are dense condensed phases, right? And they are not much different. So my denominator is going to be very, very small, which means dp by dt, the slope is going to be really huge. And that's why the slope is the maximum for the solid liquid equilibrium line, right? So can we actually do some bit of maths and get this slope? Perhaps yes. So I have dp integral P star to P. P star is my starting pressure, and on this particular line, so let's say some P star to next P, which is very close by, of course. I want to see the slope of this, and I'm assuming that delta H and delta V do not change much with temperature. Although that's not true, they do change, but the deltas would change even less, right? At a given temperature, at the next temperature, the difference would be even low. They would change, and we could take care of that if we really want to, do it more accurately. So delta H of fusion by delta V of fusion integral dt by T, right? Yeah. So assuming that they do not change much, so I have just brought it out of the integral. And that, if I integrate, I would get P minus P star equals delta H fusion delta V fusion
dt by t would be log t. Oh, t star to t, right? So that would be log of t by t star. And I know that the temperatures are not too far apart. The slope is very steep. So I could do some bit of trickery over there, and since I know that log of 1 plus x, for x being a very small number, right, between -1 to 1, I can write that as approximately x. So if that is the case, then I make this of the form 1 plus x, which means 1 plus t minus t star by t star, and the log of this number would be equal to t minus t star by t star. So my equation comes out to be p is equal to p star plus delta H fusion by delta V fusion times t minus t star by t star. Okay, I guess that should be the right one. Right. So that's the equation of a straight line. Right. Only variable is p. P star is the initial temperature. P star is the initial pressure. And final pressure is P, and it's related linearly with T. So that's why which means I can reproduce this solid liquid equilibrium line very easily. All I should know is the value of delta H of fusion and delta V of fusion, all thermodynamic properties, nothing more. If I know that, I can get the solid liquid equilibrium very easily. What about the transformations with the vapor phase? So let's look at the liquid vapor, that is boiling, right? So what does it give me? dP by dt would be equal to delta H evaporation by T delta V vaporization something. And what I realize over here is, that delta V vaporization is molar volume of the gas minus molar volume of the liquid. And liquid is a condensed space, so I can actually ignore it because the gaseous volume is much larger than it. So let me ignore that volume of the liquid and write it like delta H vaporization by T molar volume of the gas. So to make things easier, to make life easier, let me also assume that it's an ideal gas. So remember, ideal gas cannot be condensed. But just to make these equations easier, otherwise, I could take a van der Waals gas, get all the AB constants everywhere, and make life hell for everybody. But let me take it the simple way and assume that we're dealing with an ideal gas. So that would give me molar volume should be equal to RT by P. So which is equal to delta H vaporization over RT square by P. So P goes on the top here. Okay, RT by P. Which means I can bring that P over here, so that would be dP by P. Which essentially I can write as d log P, which is equal to delta H vaporization by RT square. D. Thanks. So this particular equation has some assumptions over there, right? That the volume of liquid I have ignored. The other thing is that I have assumed it could be an ideal gas. So let me write that ideal gas. This particular equation is known as the Clausius-Clapeyron equation. I'm sure you've heard of this one. And now all we need to do is to integrate it. So integral from P star to P. Oh, now if I wish to use d log P, then it should be log P star, right? So log P. D log P is equal to delta H vaporization by RT square, just a moment, RT square